Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 24th, 2026, just 4 days ago. It puts the diligent learner framework to the test, revealing that while purely internal reasoning degrades rapidly with task depth, models that build and use tools can maintain a stable success probability. The paper is titled, Tool Building as a Path to Superintelligence. And as we'll see in the breakdown later, the implications for achieving general superintelligence are quite significant. To start with the core concept, Figure 1 illustrates the diligent learner framework using a mathematical proof as a search tree. At the top, node 0 defines the problem. The left branch shows a failed attempt, where the model tries an inequality argument, gets stuck, and has to backtrack. Then, the right branch explores modular arithmetic. It hits a small dead end with k equals 2, but eventually finds the correct solution path using k equals 3. This visualization emphasizes that robust reasoning often requires navigating a tree of possibilities rather than just generating a single linear chain. So, Figure 2 takes that concept and formalizes it as a validator-guided depth-first search. Starting from the problem state at h0 on the top left, the model iteratively extends the reasoning chain. If it makes an error, shown here by the branch extending to the right that hits a fail block, it triggers a backtrack mechanism. The dashed line represents this recovery, jumping back to h1, which is the last correct state. The efficiency of this whole process hinges on gamma, the probability that the next step is a good extension, ensuring the system eventually reaches the validator and the golden solution at the bottom right. So, Figure 3 puts hard numbers on that concept. Here, we see how the step success probability, gamma, scales as the reasoning chain grows deeper. The blue line at the top represents the ideal estimator A. Because it uses both the full history and new evidence, it maintains a perfect success rate. However, the orange and green curves tell a different story. These represent estimators relying on partial information, like using only current data. They crash almost immediately, dropping to the random baseline shown by the dashed line. This confirms that without tracking the complete state, deep reasoning becomes impossible. Well, while the previous figure established theoretical limits, Figure 5 puts real small language models to the test. This chart plots the step success probability, gamma, for the Qwen3 family as the reasoning depth increases from 1 to 31. The green curve highlights the 30 billion parameter thinking model, which starts with a distinct advantage at shallow depths. Yet notice how it rapidly degrades, mirroring the decline of the instruct models in purple and orange. By the end, all trajectories converge toward the black dashed line of random guessing, confirming that without external tools, these models lose track of the state needed for deep reasoning. Alright, Figure 6 expands the scope to compare those struggling small models against frontier systems like GPT 5.2, Claude Opus 4.5, and Gemini 3 Pro. The vertical axis uses a logarithmic scale to plot the probability of correctly deducing a step. On the left, the bars for the 4B and 30B models barely clear the dashed line, which marks the baseline for random guessing. In stark contrast, the frontier models on the right perform orders of magnitude better, with the tool-enabled versions shown as solid bars, often reaching near-perfect reliability at the top of the graph. So, Figure 7 investigates the impact of tool use at much deeper reasoning horizons, specifically 63 and 127 steps. The solid bars represent models using tools, like ChatGPT and Opus, which maintain a success probability near 1 even at these extreme depths. In contrast, the hatched bars show the no-tools performance, which crumbles as the task gets harder, often falling toward the random guess baseline shown by the dashed line. This gap proves that externalizing state tracking, essentially offloading memory to tools, is what prevents the reasoning collapse. Okay, to understand exactly why the small models collapse, Table 1 fits their accuracy to a theoretical memory model. The variable u in the first data column represents the fraction of the history the system effectively retains. In the second row, the 30B thinking model reaches a u value of 0.47, meaning it captures nearly half the context. This is a clear step up from the instruct version in the top row, which sits at just 0.15. However, since neither value is close to 1, it confirms that without tools, even the best small models act as partial information estimators, inevitably losing track as the reasoning chain extends. Wrapping up, the big takeaway is that internal reasoning has a hard limit. As tasks get deeper, models lose the thread unless they can offload memory. The path to superintelligence, therefore, isn't just about bigger brains, but about building tools to verify and track complex states. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.